Good morning, everyone. Today we will continue to talk about rain opticals. And yeah, that's yesterday we talked about the rim opticals. We talk about the rim model for the light, and talk about the reflected refraction, reflection, and refracted and refraction. Yeah, so those two words are very similar, so don't mix them together. Okay, today we will continue to focus on RAN opticals. Let me share my screen. Okay, yeah. Yeah, last yesterday we talked about the goal for chapter 80 is to understand and apply the rain model of light. Yeah, in chapter 17 we mainly focus on the wave model of light, and in chapter 18 we mainly focus on the rain model of light. Yeah, okay. This is today's goal. Firstly, we will review a reflection, refraction, and the rain model of light. And after that, we will learn thin lenses and rain tracing. And then we will explore image formation with spherical mirrors. And finally, we will understand the thin lens equation. Yeah, this is today's goal. Yeah, and let's continue. Yeah. Firstly, let's talk about, let's review something about reflection. Yeah, this is uh, the law of reflection. Like this is a incident, this is an incident light angle, and this is a reflected angle. And you can see this angle and this angle, they equal with each other. And this is what? To remember that this we call it norm. This line perpendicular to the surface. Yeah, and a reflection can be specular, like a mirror, like or diffusion. Yeah, from rough surface. Yeah, reflection can be specular or diffuse. Like plane mirrors. Yeah, a virtual image is formed at this p dot with s dot equal s. Yeah, this distance and this distance is equal, where s is the object distance and s2 is the image distance. Yeah, so this is we talk about the reflection, and then let's talk about review something about the refraction. Yeah, for the refraction, we talk about the Snell's law of refraction. You can see here, this is the incident ray, and this is the refracted ray, and this is the norm line, and this is the incident angle. This is a refracted angle. Yeah, there is a relationship between the this material and this material. Yeah, the N1 sin theta 1 equal N2 sin theta 2. This is Snell's law. This law is very important. Yeah, we can use this equation to calculate the index of refraction. Yeah, the index of refraction is N equals C divided V, and this C is the light speed in vacuum. Yeah, we know that it is 3 multiple 10, yeah, per second. Yeah, the ring is closer to the norm on the side with a larger index of refraction. You can see if the like a refraction is larger, yeah, which means this one will be smaller. If you want to this one equal this one, doesn't make sense to you. Yeah, like if N2 smaller than N1, yeah, if this one smaller than this one, yeah, like the total internal refraction, we call it TIR, occurs when the angle of incident theta 1 is greater than theta c. Yeah, we also like talk about how to calculate theta c and the total internal reflection, which means there will now like a refracted like a lens. It is reflected is just 90 degree, and it all like reflected. Yeah, doesn't make sense too. This is a total internal like a refraction. Yeah, this is something we talk about refraction. And also we talk about the Rain model of light. The light travels along straight lines called light rays at speed v equal c divided n. And the light rain continues forever. A nice interaction with matter causes it to refract, scatter, or be observed. Um, Light rays come from self-luminous or reflective objects. Yeah, we call it, we talk about what is self-luminous, what is reflective objects. And for the self-luminous, there are four different kinds, like the point source and the extended light source and the full source. You can review them. And the reflective objects, which means like itself cannot emit the light. It just reflect the lights from other source like that. Each point on the object sends rays in all directions. Yeah, and rain diagrams use only a few slight rays to represent all the rays emitted by an object. For example, here, this is a rain diagram. Actually, there not only those 2 points emit like lights. This is just like use those 2 points to talk about like how to analyze this image like that, how to analyze this situation. Yeah, in order for the eyes to see an object or image, like rays from the object or image must enter the eye. Yeah, we'll talk about this. Yeah, if the light didn't enter the eye, which means you cannot see it. Yeah, this is a rain model of light. Yeah, this is what we mainly talk about in NASA class. Yeah. In this class, we will talk about, we will continue to talk about the rain like a model of light, but other things. The first things we talk about the thin lessons like a rain tracing. Yeah, for the thin lessons and the rain tracing like a lens. Yeah, is a transparent material that uses refraction of light rays at curved surfaces to form an image. Yeah. Rain tracing is a pictorial method used to understand image formation. A convergent lenses, yeah, you can see here. The convergent lenses causes the rays to refract toward the optical axis. Yeah, this is a usually this is the optical axis, and this is a convergent like a lens that cause the rays. You can see different rays to refracted toward the optical axis. Yeah, and a divergent lens, like this is a divergent lens. Yeah, causes the rays to refract away from the axis. You can see this is a like a axis, and it will from away from to refract away from the axis. Yeah, this is a divergent lens. Yeah, you can see for the for this convergent lessons, yeah, which are thinner, yeah, in the center than at the edges. Yeah, so it can refract parallel lines towards the optical like axis. But for the divergent lessons, and like which are the thinner in the center than at the edge, then like this like divergent lessons will refract parallel lines away from the optical axis. Does it make sense to you? Okay, let's continue to talk about the thin lenses. Okay, in a convergent lens, an incoming ray refracts towards the optical axis at both their first air-to-glass boundary and the second glass-to-air boundary. Yeah, you can see here. Actually, there are two boundaries. This is one boundary. This is the other boundary. And yeah, like in a convergent lens, and this is an income ray refracted toward the optical axis at both, like not only this boundary, but also this boundary. They will like they both like refract towards the optical axis. Yeah, does it make sense to you? Because if you draw the norm, let's try to draw the norm. Yeah, this is the surface, and if this is the norm, you can see, because yeah, the index of refraction will is bigger than the air, so which means this this angle is smaller. Am I right? So which means it will like it will become smaller, then go to this direction. Yeah, from this one to from here to from like this one to this one, and it which means the index of refraction will become bigger, because will become smaller, which means will become smaller, which means this angle will become bigger. Yeah, so which means this one should be bigger than the one, and then it will like go to this direction. Does this make sense to you? Yeah. Yeah, this is like for a convergent lens. Okay. The incoming rays initially parallel to the optical axis converge at the same point. Yeah, this point. Yeah, this point. Yeah, like we name this point the focal point of the lens. The distance of the focal point from the lens is called the focal length f of the lens. Yeah, this distance we call it focal length, and we use f to represent it. And this is we call it a focal point. The curvature of the surface and the index of refraction of a particular lens determines the focal points and the focal length. Yeah, like there are two different things to determine the focal points and the focal length. The first one is the curvature of the surface, and this is the first one. The second one is the index of refraction of a particular lens. Yeah, these two determine the focal points and the focal length. Yeah. Okay. Like okay, sorry, I think I just repeated these things. Okay, and the lens in a like we just talk about the like a convergent lens, and let's talk about the divergent lens. Yeah. Yeah, the lens in a divergent lens causes the rays to refract away from the axis. Yeah, you can see this is a parallel like a rays, and through the divergent lens, and the light rays will like refracted away from the axis. A backward projection of the rays shows appear to have started from the near focal point. Yeah, a backward projection of the rays shows appear to have started from the near. This is the near focal point. rays appear to divergent from this point. Yeah, you can see if you connect those refracted lines, and you can see it will converge in a line, in a point. We call this near focal point. For both types of lenses, the focal length is the distance from the lens to the point at which rays parallel to optical axis converge, or from which they appear to diverge. Yeah, does this make sense to you? Like for the like a convergent lens, the vertical length is the distance from the lens to the point, which like for this point, this like a focal point, and for the for this point, the like focal point, and for divergent length, and the focal length is the distance from the lens to from the lens to the like near focal point, which the near focal point is the like the refracted lens converge to the like converge to one point, like it is from which they appear to diverge. Does it make sense to you? Yeah, this is the definition for focal length. Yeah, definition for focal length. Okay, yeah, let's continue to talk about more details about converging lenses. A thin lens is an idealized lens whose thickness is zero, and that lies entirely in a plane called the lens plane. Within the thin lens approximation, all refraction occurs as a range across the lens plane, and all distances are measured from the lens plane. And there are three situations from the basis for ray tracing. Firstly, rays parallel to the optical axis will refract through the far focal point, and rays passing through the near focal point emerge from the lens parallel to the focal axis. And the next one is rays directed at the center of the lens pass through in a straight lines. Yeah, let's talk about those two different like situation. Sorry. Yeah, those are the three different like lens. Yeah, the first one, yeah, you can see any ray initially parallel, initially parallel to the optical axis will refract through the focal point on the far side of the lens. Yeah, this is the far focal point, and like those parallel lens will like converge to this point. And the second one is any ray passing through the near focal point. You can see there are like some lens they passing through the near focal point, and from the lens, from the convergent lens, and the refracted lens will like will be like the parallel line rays, like they parallel to the optical axis. Yeah, and the third one is any ray like directed. You can see directed. This is the center. At the center of the lens, passing through in a straight line. You can see it is in a straight line. Yeah, this is for the convergent lens. Yeah, the three situations from the basis for reinforced for tracing for like a convergent lenses. Okay, like yeah, let's talk about the for a real image. What is a real image? Like if rays diverge from an object at point P. Yeah, you can see here. If rays, yeah, you can some rays diverge from an object at a point P, this point P, and enter interact with the lens, and interact with the lens, such that they converge at point P dot, like, then we call P dot a real image of point P. We call this point is a real, we call it a real image of point P. 3 spatial rays, one parallel to the optical axis, one through the center, and one through the near focal point. You can see there are 3 lanes. This one is just a parallel like to the optical axis, and this one is the one through the center, and this is the one one through the near focal point. Those 3 spatial rays always can be converged into this real image point. All points on the object that are in the same plane, the object plane, converge to the image points in the image plane. This is the image plane. And it will convert to the image points in the image plane. Does it make sense to you? Okay. This is some definition for the real images. Okay, like let's talk about one application. The image is called an inverted image because it is upside down. You can see this one. It is upside down. That makes. Do you see that? And the image called an inverted image because it is upside down with respect to the object. It is a standard characteristic of real image formation. For real image formation, like we know that for now, like the real image formation, it is always a inverted image. So it is upside down image. Rays from point P fill the entire lens surface. A larger lens connects more rays and therefore makes a brighter image. This is just some like a character feature. The rays from point P fill the entire surface. This one, fill the entire surface. And a larger lens collects more rays and therefore makes a brighter image. If the when the converged lens bigger and bigger, and the brighter the real image will brighter and brighter. Does that make sense to you? Okay, the rays don't stop at P dot. A nice piece screen in the image plane. When we do, the image is sharp and well focused. Actually, you can see, the rays will not stop here. So will not stop here. It will go on. If we put like a screen here, then there will be a sharp image. Sharp and well focused image. If the screen is placed other than the image plane, an image is produced but is blurred and out of focus. You can see if this is, we put an image plane here, here, and the image is focused and sharp. But if we place the image plane here, before the before the P dot or after the P dot, and the image is although the image is produced, but it is blurry and out of focus. Because the rays don't stop, and it doesn't make sense to you. Okay. Let's talk about the tactics box 80.2, like how to do a ray tracing for convergent lens. The step one. Firstly, we draw an optical axis. Use graphic paper or a ruler. Establish an appropriate scale. First, step 2, center the lens on the axis. Draw the lens plane perpendicular to the axis through the center of the lens. Mark and label the focal point at a distance f on either side. You can see there will be a like a far focal point and the near like a focal point. Yeah, represent the object with an upright arrow at distance s. It is usually best to place the base of the arrow on the axis and to draw the arrow smaller than the radius of the lens. Yeah, represents the object with an upright arrow at a distance s. Yeah, you can see here in this equation, in this draw, yeah, you can see you can draw every you can like label every details each. This is eyes, and this is the focal and near focal point. This is a far focal point, and this is image plan. Yeah, image plan distance. Yeah, this is image height. This is object height. Yeah, you can label everything you want. And step 4, draw the 3 special rings from the tip of the arrow. Actually, there are so many rings, but you just need to like draw the 3 special rings from tip of the arrow. Yeah, use a straight edge or a ruler. The rings reflect at the lens plane, not at the surface of the plane. Yeah, reflect. That makes sense to you? Yeah, the rings refract at the lens plane, not at the surface of the plane. You can see here. Yeah, actually, this is the lens plane. Yeah, this is the lens plane. Yeah, the refracted happens here. The refraction happens here, not here, not here. That makes sense to you? Yeah, this is just a idealized situation. Yeah, okay. And for the 3 special rings, yeah, there are 3 different like special rings. The first one is a ring initially parallel to the axis refracts through the far focal point, and the second is a ring that enters the lens along a line through the near focal point emerges parallel to the axis. And the next one is ring through the center of the lens does not bend. Yeah, we just draw those 3 kind of like ring. Yeah, you can see. Yeah, just in this image. Yeah, like these 3, this one and this one. Yeah, and this one. You can see this one is just a straight line, and this one is just like a converge to the like image point. Yeah, and this one is just like go through the near focal point and then parallel to the optical axis and to the image point. Does that make sense to you? Okay. And the step 5 is extend the rings until they converge. Yeah, the rings converge at the image point. Draw the rest of the image in the image plane. If the base of the object is on the axis, then the base of the image will also be on the axis. Yeah, just extend the ring until they converge. You can see here. Yeah, when you draw the ring to here, it's not finished. You need to let them to converge to here. Yeah, does it make sense to you? Okay. And the next step, like mirror the image distance as dot. Also, if needed, mirror the image height related to the object height. Yeah, the magnification can be found from equation 90.9. Yeah. Yeah, we will talk about equation 90.9 later. Yeah, this is just like the steps for like how to find the ring tracing for converging lenses. Yeah, okay, let's continue. Let's talk about one example, like 80.7, finding the image of a flower. A 4 centimeter diameter flower is 200 centimeter from the 50 centimeter focal length of a camera. How far should the plane of the camera's light detector be placed behind the lens to record a well-focused image. What is the diameter of the image on the detector? Yeah, this is just what we need to. You can see, firstly, you need to, first step, you need to like lay out the optical axis with a scale. Yeah, and then you draw the lens and the lens plane and mark the focal points. You can see here is a near focal points. Here is a far focal points, and this is a focal length. Yeah, and next step, draw the objects as an arrow with its base on the axis. Yeah, this is the like object, and this is a yeah, and this is the height of the object. Yeah, it is 200 centimeter. Yeah, and the next step, like draw the 3 special lines from the tip of the arrow. Yeah, you can see the first one is the parallel to the axis. Yeah, and then converge to this is the image point, and the second one is through the near focal point. Yeah, this is through the near focal point, and then go to the like lens, and then parallel to the optical axis, and then converge to the image point. And the last one is through the center. Yeah, you can see it is just through the center, and then convert to the image point here. Yeah, and next step is the convergence point is the tip of the image. Draw the rest of the image. Yeah, you can see, you can draw the rest of the image. This is a H dot, and the last step is just a mirror the image distance. You can see, you can mirror this distance. Yeah, then you can get the distance. Like you can get the how far should the plane of this is how far. Yeah, and also what is the diameter of the image on the, this is H dot. Yeah, you also can know that. Yeah, we will use the ray tracing following steps of tactics box 42.2. Yeah, this is what we want to use. Yeah, and and to find the location of the image, we start with an accurate drawing of the situation, scaled so that 25 centimeter correspond to 1 centimeter on the diagram. You can see here, this is one is 25 centimeter. So which means 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is 8. Yeah, which means this is I'm sorry. This is 200 centimeter. Yeah, this is the flower, the distance between the flower and the lens. Yeah, it's 200 centimeter. Okay, like we start with yeah, and let's try to resolve this problem. The figure shows the range tracing diagram and the steps of tactics box 80.2. The image has been drawn in the plan. Yeah, you can see this image has been drawn. Yeah, and where the 3 special rays converge, you can see from the drawing. Yeah, you can see it is 1, 2, 3. Am I right? It is like you can see from the drawing that the image distance is around like 25, and yeah, this is 1, yeah, 1, 2, 3. This is 3, but it's not like like close to it's close to 3, but not reach to 3. So which means this is 75. It's around like 65 centimeter. Does it make sense to you? Yeah. Okay. And this is where the detector needs to be placed to record a false image, and the height of the object and the image are labeled H and H dot. These are respectively the diameter of the flower and the diameter of the flower's image. The rays through the center, you can see the rays through the center of the lens is a straight lens. Thus, the object and the image both subtend the same angle theta. You can see here. This is the theta, and this is the theta. Yeah, does that make sense to you? Yeah, which means yeah, this one, yeah, this, yeah, and which means yeah, this one H divided HP should equal what? Should equal S divided SP. Yeah, because you can see these two triangle. Yes, here it has the same angle here, it's the same. So which means the this one and this one and this one and this one, they should be the same ratio, have the same ratio. Yeah. So we have this equation. Yeah, and from the similar like triangles, yeah, the similar triangle, I think you have already learned this in like high school or like some the basic mathematics class. Yeah, yeah, we have this equation. Actually, you can see it should be h equal h or s equal s, but it's the same thing. Yeah, so then we can like solve for h like h will equal what? H divided as multiple s dot, yeah, which means this is 4 centimeter and this is 65 and this is 200 centimeter. So and the h dot should around like 1.3 centimeter. The flower's image has a diameter of 1.3 centimeter. Yeah, as says this question, the ray tracing process we have outlined and has a built-in check. The first two rays converge at a point. The third ray should converge at the same point. If it doesn't, there is an error in our work. In this case, all three rays converge at the same point, so we can have a confidence in our result. Yeah, you can see those three. Let me try to. Yeah, those three lines. This one, this one should converge into one point, one image point. Otherwise, there must be something wrong. Yeah, does it make sense to you? Okay. Okay, let's talk about magnification. Like the image can be larger or smaller than the object, depends on the location and the focal length of the lens. The magnification arm combines the image size and the orientation of the image relative to the object and its size. Yeah, this is the magnification of a lens or a mirror equation. The arm equal negative S dot divided S. Do you know what is S and S dot? Yeah, actually, let us to talk about that. Yeah, this one. Yeah, the S is the distance between the object with the lens. Yeah, this is S. And the S dot is the lens, the distance between the lens and the image, like a object image. Yeah. That makes sense to you? Yeah, this is S dot. So yeah. So the magnification is equal negative S dot divided S. Yeah. Like the absolute value of M gives the ratio of image head to object head. You can see here. It is the like a image head, like the ratio of image head and to the object head. Yeah, that makes sense to you. Yeah, and a positive value of m indicates that the image is upright relative to the object. Yeah, a positive value of m indicates the image is upright relative to the object. A negative value of the m indicates the image is inverted. Yeah, which means you can see here, this one, like the m equal equal no yeah, like here I star equal s is like it's positive, which means it is upright. Yeah, but here we have they haven't defined the m, so we just ignore the m. But if you want to like calculate this magnification, and you need to use like a negative. You need to use negative h dot divided h. Am I right? Or s dot divided s. Yeah, and this is just a negative for this image because it is the image is invert. So which means the magnification should be negative. Yeah. That makes sense to you? So this is the definition for the magnification. So the magnification is just the the ratio of image height to the object height. Yeah, also like a distance of image object to the lens to the like image to the lens. Yeah, that makes sense to you. This is the definition for the magnification. And let's talk about the virtual images. Yeah, actually we talk about the real image here, just before like yeah, the real image. Yeah, which means the real image is what the like yeah. Then we call this one is a real image, which means the real image is inverted. Yeah, with like compare with object like the original object, and the virtual image. Let's talk about that. When the object is inside the focal point, yeah, here is object. Yeah, this object this is the focal point. It's inside the focal point. A ray passing through the focal point, which means if there is a ray passing through here and passing through like here and maybe here, yeah, like to the left would never reach the lens. You can see those rays will never reach the lens. That makes sense to you because the lens is here. Yeah, opposite direction. Yeah, that makes sense to you. Okay. So the rays emerging parallel to the axis, entered the lens along a line passing through the near focal point. Yeah, the ray you can see emerging parallel to the axis enter the like lens. Yeah, you mean this one? Yeah, because it parallels optical x enter the lens along a line passing through the near. This is the near focal point. Does it make sense to you? Yeah. So this is like what is like a virtual image when the object you can see is inside the focal point, and like those directions rings will never reach the lens, reach to the lens, and also the rays emerging parallel to the axis entered the lens will along the line passing through the near focal point. And the three refracted rays do not converge. You can see these three like refracted rays. Yeah, this one. Okay. Yeah, this one and this one and this one. Yeah, they will now like converge, and the rays appear to diverge from point P dot. Yeah, you can see those three lengths. Yeah, they appear to diverge from point P dot, and the rays appear to come from the point P dot, but none of the rays were ever there. Yeah, it appeared to come from P dot, but it's not. Yeah, the point P dot is a virtual image of the object point P. Yeah, it so so we call this point P, and this image we call it is a virtual point image, and it is an upright image. Yeah, you can see it is just the object is upright, and also the virtual image is also upright, because no rays actually pass through like a P dot. Yeah, placing a screen at the image plane would not produce an image. Yeah, you can see if you place a image plane here, there will not produce an image, because actually those rays not like are not from here. Yeah, does that make sense to you? Yeah, this is a virtual image, the features for the virtual images. And your eyes can see a virtual image. This is what happens when you look through a magnifying glass. You can see, yeah, your eyes can see this virtual image. But if you place a screen here, yeah, in this screen there is there is nothing there. Yeah, the magnification arm equal negative s pair like s dot divided s is positive, because the virtual image is upright. Yeah, that means the ratio s dot divided s must be negative. That makes sense to you? Yeah, like we define the image distance as s dot, like this one to this one, yeah, to be negative for a virtual image. Yeah, this is our first sign conversion for lenses. Yeah, this is just some definition. We just define the image distance as though is negative for a virtual image. Yeah, this is the eyes. Yeah, and you can see like this is an example, like your eyes can still see a virtual image. This is what happens when you look through a magnifying glass. Yeah, that makes sense to you. Yeah, you can see a virtual image here, but if you put a screen here, nothing will display here. Doesn't make sense to you? Okay, and let's talk about one example, finding the image for a convergent lens. Yeah, to see a flower better, you hold a 6 centimeter focal length magnifying glass 4 centimeter from the flower. What is magnification? Which means here from the object to the lens, it is 4 centimeter, and you hold six like a 6 centimeter like focal length magnifying glass. Yeah, which means this focal point, the distance from like lens and the focal point is 6. Yeah, this is 6 and this is 6. Yeah, what is a magnification? Yeah, let's talk about that. The flower is in the object plane. Yeah, use ray tracing to locate the image. Once the image distance is known, equation 80.8 can be used to find the magnification. Yeah, this figure shows a ray tracing diagram. The three, yeah, those three special like rays diverge from the lens. Yeah, diverge from the, but we can use a straight edge to extend the rays back forward to the point from which they diverge. Yeah, like this. Does it make sense to you? Okay. This point, the image point, yeah, like this point. This is the image point, P dot. Yeah, it is it's seen to be 12 centimeters to the left of the lens. Yeah, this is a question. yeah, you can see here is after we diagram that draw a diagram. Yeah, this is if you just put this yeah to the here and put this to here and put this to here, and you know will know this is 12 centimeter, and to the left know the length, because this is a virtual image. The image distance is it's negative. Yeah, we have already talked about it should be negative. The still equal negative 12 centimeter. From the equation 90.9, the magnification is m equal negative s dot divided out and equal what? This is negative and this is also negative, and s equal 4. We have already talked about. Yeah, this is 4. Yeah, we have already yeah, this is the question I have given to you, and then we can get the magnification is 3. Yeah, the 3 special ranges convert to a single point, and the image orientation and size in our ray tracing diagram match the computed magnification. The image is upright and much larger than the object, so we have confidence in our result. You can see when you use the magnifying glass, you want to make the object bigger. Am I right? You can see the virtual image is much bigger than three times bigger than the object. Yeah, does it make sense to you? Yeah. Okay, let's continue. So let's we have already talked about the convergent lens. Let's talk about divergent lenses. Yeah, a divergent lens is one that is thinner at its center than at its edge. Yeah, divergent lenses always make virtual images. Yeah, it will not make real images. It will always make a virtual image. Virtual image is just like it is upright. Yeah, image. And the ray tracing follows definite text box 18.2, except that two of the 3 special ranges in step 4 are different. Yeah, let's review the box 18.4. Yeah, here first you draw an optical axis and then center the lens on the axis and represent the object with an upright arrow at distance s, and draw the 3 special ranges from the tip of the arrow, and then extend the ranges until they converge and mirror the image distance as well. Actually, yeah, the difference between the convergent and the divergent, the difference is just those 3 special ranges. Yeah, so let's continue to talk about the yeah for the because the only difference is just except that 2 of the 3 special ranges in step 3 are different. Yeah, those 3 different special ranges. One range is initially parallel to the optical axis, then diverges along a line that would extend back through the near focal point. Yeah, and the other one is directly on the line toward the far focal point, but emerges parallel to the optical axis. And one is directed at the center, and like convergent lenses pass through in a straight line, which means yeah, compare with convergent. Yeah, this one is the same thing, and the other 2 are different. Yeah, we can see this. Yeah, and for divergent lenses, yeah, the first is just like a parallel line, but it will diverge to different after goes diverge after this lens. Yeah, and this like a diverging lens will if you connect them together, it will converge into the near focal point. Yeah, and the second situation is any ray directed along a line toward the far focal point emerges from the lens parallel to the optical axis. And if those lens those rays like they toward to the far focal point, and after the lens, they will like form a parallel lens. Like those parallel lenses are just parallel with the optical axis. And for the like any ray directed at the center of the lens passes through in the straight line. It's the same thing with the convergent lenses. Yeah, does it make sense to you? Okay. Okay, let's talk about how to do ring tracing for a diverging lens. And the first three steps is just like just similar with the ring tracing for convergent lens, like exactly same with text box 80.2. Okay, let's do a review. Let's try to find 80.2. Yeah. Yeah, for the first three steps, we'll like draw an article axis. Use graphic paper or a ruler, establish an appropriate scale. And the second, and center the lens on the axis. Draw the lens plane perpendicular to the axis through the center of the lens. Mark and label the focal points at distance f on either side. Yeah, one is a near focal length, the other is a far focal length. And the step 3 represent the object with an upright arrow at distance s. It's usually best to place the basin of the arrow on the x and to draw the arrow smaller than the radius of the lens. Yeah, those three steps is similar, just the same for the divergent lens. Okay, let's continue to talk about the ring tracing for. Okay. Yeah, sorry. And from step 4, and there are some difference. Like draw the three special lines from the tip of the arrow. Use a straight edge or a ruler. The lines refract at the lens plane. And there are three special lines, and those three special lines are different with the convergent lens. Yeah, the first one is a line parallel to the x. They diverge along a line through the near focal point, and the second, a line along a line towards the far focal point emerges parallel to the axis, and the third, a line through the center of the lens does not bend. Yeah, it's just like those three lines. Yeah, and the step 5 trace the divergent lines backward. The point from which they are diverging is the image point, which is always a virtual image. Yeah, we like you can see here those like those lines. If you just extend to opposite direction, it will let you to get the virtual image. Yeah, this is for steps 5 and the next step mirror the image distance as dot, which because the image is virtual, we will take as a negative number. Also, if needed, mirror the image height relative to the object height. The magnification can be found from equation 80.9. It's just like the exactly, let me show it to you. Yeah, this one. Yeah, we can find the magnification using this equation. That makes sense to you? Okay, let's continue to talk about. Yeah, okay, let's check some quick check questions. The first one is you can see the sound range and lens to start a fair. To do so, you should use a convergent lens or divergent lens, or either a converging or diverging lens will work if you use correctly. Actually, I think this one is easy. If you want to use sound range to and a lens to start a fair, you need to let all the light uh, converge to a point, and then this point will have the all the energy of those light rays, and then start a flare. So the answer is obvious. It should be a convergent lens. That makes sense to you? Okay, yeah, the answer should be A. And let's check the other one. A lens produces a sharply focused inverted image on a screen. What will you see on the screen if the lens is removed? Yeah, this is the object. Am I right? And this is a lens, and through the lens, and this you have the you have you have a real image. Yeah, and if this lens is removed, what will you see in this screen? What will you say? Think about that. Actually, yeah, no image at all. Yeah, because if you remove this lens, which means there will no like this real image here, because the light is just like a this image is just like a it cannot form this real image in this screen. Does it make sense to you? Yeah. And let's check the other one. A lens produces a sharply focused inverted image on a screen. Yeah, this lens produces a sharply focused inverted image on screen. What will you see on screen if a piece of dark paper is lowered to cover the top half of the lens? Which means top half of the lens. Yeah, A, inverted but blurry image. B, an image that is dimmer but otherwise unchanged. C, only the top half of the image. D, only the top half of the bottom half of the image. E, no image at all. Yeah, which one? It just cover this one. Actually, you can see like all the light also can like through the lens. Yeah, so what you can get is just an image that is dimmer but otherwise unchanged. Yeah, because although you covered the half the lens, and the light you, still can through the lens. The sunlight can still through the lens and form this image, but not so much like light rays. Yeah, yeah. If it is a whole like a lens, there are so many like rays to through this lens. But if you cover it, it's just half of like light rays. Does that make sense to you? Okay, let's talk about the other one. A lens produces a sharply focused inverted image on a screen like this. What will you see on the screen if the lens is covered by a dark mask having only a small hole in the center? Yeah, which means it's just like a there is only this lens will be covered, and there only one hole here. So what's the answer for this one? Yeah, actually, yeah, it is still B, because only if there is even if there is only one like a hole, yeah, the object like also can have the rays to go through this like a hole, and can form a inverted image on this screen. Yeah, but like I said, not too many like rain go through these holes, so the image will be dimmer, but otherwise unchanged. That makes sense to you? Okay. Let's talk about this one. Which of these rays diagrams is properly correct? Yeah, you can see based on what we have already learned, all the like light rays go through the center will not change the direction. Am I right? So which means that this one is not right, this one is not right. Yeah, we need this and this. And since this one is a convergent like a lens, yeah, based on the shape, this one is a convergent like a lens. So it should through the convergent lens, it should converge to a point, a focal length point. Does it make sense to you? So the answer should be D. Does it make sense to you? Okay. Yeah. Okay, let's continue to talk about one example. Finding the image location for a divergent lens. A divergent lens with a focal length of 5 centimeter is placed 100 centimeter from a flower. Where is the image? What is its magnification? Yeah. Okay. The first thing, what we need to is just draw the diagram. Yeah. So for this diagram, this is the object. Yeah. You just use arrow, and this this is the divergent lens, and with a focal length 50 centimeter, which means yeah, we just use this is 25. So this is 50 meters, 50 centimeter. This is like a far focal point. This is the near like a focal point, and then you can draw three special rings, and then those three special rings, and this one should like this one should parallel to the after the lens is parallel to the axis, and this one is just goes straight, and this one is just like a parallel, and then like a diverge, and but those three lens, those three, if you draw like them, it will like converge to this side. This is just the image, the virtual image. Yeah, it will be here. So where is the image? The image is this is like the 25 centimeter. Maybe there is about 12 or 10. So which is 3 centimeter, 35 centimeter, like behind in front of the lens. Does it make sense to you? Okay, let's talk about it more. And the flower is in the object plane, and use ray tracing to locate the image. Then we use equation 18.9 to find the magnification. The figures, yeah, we need to like draw these figures. The figures show the ray tracing diagram. The three special rays labeled ABC, this ABC, to match the textbook box do not converge. Like, however, they can be traced backward. Yeah, they can backward. Yeah, to an intersection around 33 centimeter to the left lens. Yeah, we talk about it's around 35. It's close. Yeah, it's just around the value, and because the rays appear to diverge from the image, that is a virtual like image, and s star smaller than 0. Yeah, the magnification like based on the equation. Yeah, we know it's this one. Yeah, for now we know this is just around like 35 or 33. Yeah, 35 to 33, and this is what this is 100. We have already the question has given it to you. It's placed 100 centimeter from a flower. So like we can get the magnification like using this equation, and then we can get the magnification is 0.33. And the image which can be seen by looking through the lens is 1/3 of the set, 1/3 the size of the object and upright. You can see that this is a virtual image, and it is third. It is smaller. It's not bigger. It is smaller, and it is around like 1/3 of the size of the object and upright. Yeah, the three spatial rays appear to diverge from a single point, and the image orientation and size in our ray tracing diagram match the computed magnification. The image is upright and smaller than the object, so we have confidence in our result. Does it make sense to you? Because this match what we draw. Yeah. Okay. Let's continue to talk about something different, like section 18.6 image formation with spherical mirrors. Yeah, like spherical mirrors are curved mirrors. You can see it's not flat. Yeah, we talked about mirrors before, but it's flat. Yeah, but here it's a curved mirrors. Yeah, we call this like spherical mirrors, and this is curved mirrors and can be used to form images. Yeah, like the mirror in the figure is a convergent mirror. You can see the light, the parallel rays can be converged to this point. Yeah, this focal point. Yeah, and often called a concave mirror. Yeah, parallel like waves reflect off the mirror and pass through the focal point. Convergent mirrors often used in telescopes and searchlights. Yeah, they can like be converged into one point and make this point very like very bright. Yeah, that makes sense to you. Okay. Yeah, this mirror like is a divergent mirror. You can see it is often called a convex mirror, and the parallel rays that reflect off its surface. Yeah, those kind of mirror. Yeah, will like it will reflect off its surface, appear to have come from a point behind it. Yeah, and if you see this rays, it appear to have come from this point, from a point behind the mirror, but it is not. Yeah, divergent mirrors are often used for security and rear view mirrors. Yeah, you can see you can see more things like using divergent mirror. Yeah. Okay, let's continue to talk about. Firstly, let's talk about more things about like convergent mirrors. Yeah, three spatial rings can be used to analyze mirrors. Yeah, one spatial ring is parallel to the optical axis and reflects through the focal point. Yeah, this is the first kind spatial ring, like the parallel rings. This parallel rings does parallel to optical axis and reflect through the focal points. Yeah, and even initially parallel to the optical axis will reflect through the focal point. And the other one special ring travels through the vertical point and reflects parallel to the optical axis. Yeah, like those things. Yeah, those kind of ring travels through the focal point and reflects parallel to optical axis. Yeah, that makes sense to you. And the next one, yeah, the other one special ring is directed at the center of the meter. Yeah, and reflects at an equal angle on the opposite side of the axis. Yeah, this side angle and this angle is equal. Yeah, this is three special like ring travel special rings can be used to analyze mirrors. Yeah. Okay. Let's continue to talk about convergent mirrors. When an object's distance s from the mirror is greater than, yeah, this is the distance from the object to the like a mirror, s. This is s. It's greater than the focal length. Yeah, this is the focal length. If this distance is greater than the focal length, the three spatial ranges are enough to locate the position and the size of the image. And those three, yeah, this is one candle, and this is the other candle, and this is this three are enough to locate the position and size of image. Incoming rays reflect off the mirror plane, not off the curved surface of the mirror for the rain trace. Yeah, the incoming rays reflect off the like a mirror plane, not off the curved surface of the mirror for the rain trace. The image is real, yeah, because rains converge at the image point. Yeah, this three, yeah, it is real converge to this point. Am I right? If the object is inside the focal point, if it's inside, the image is a virtual image and is used as a magnifying mirror. Yeah. Okay. Let's talk about why, like, if the object is inside the focal like a point, the image is a virtual image and is used as a magnifying mirror. You can see if the object is here, yeah, inside the focal point, then we can draw this special ring. Yeah, it's a same ring. Yeah, from this point. For example, here is P, and then we have this ring, special ring, like goes go to like the center like a point, and then it will reflected the same angle. So this one, but you can see because it is inside the focal point, and the point, the ring go through the focal point will now get into the mirror. So what we need to do is just like a you can see those two lines will converge inside, yeah, in this direction. Yeah, this is then there will be a virtual image here. And you can see this virtual image is bigger than the original one. That's the reason why it is used as a magnifying mirror. That makes sense to you? Okay, let's continue. Yeah, this is like how to do ray tracing for a concave mirror. Like actually, it's a similar thing with like do the ray tracing for the converging lens and the diverging lens. Yeah, and the first step is draw an optical axis. Use graphic paper or ruler. Establish an appropriate scale. And second, center the mirror on axis. Yeah, for the like a lens, you just center the lens on the axis. Here is center the mirror. Center the mirror on the axis. Mark and label the focal point at distance f from the mirror surface. Draw the mirror plane through the mirror center, perpendicular to the axis. The step 3. Represent the object with an upright arrow at distance s. It is usually best to place the basin of the arrow on the x and to draw the arrow smaller than the radius of the mirror. Yeah. The step 4, like draw the 3 special rings from the tip of the arrow. Use a from the tip of the arrow. Use a straight edge or ruler. The rings should reflect off the mirror plane. And yeah, and those three is 3 different like special ring parallel to the axis reflect through the focal point, and an incoming ring that passes through the focal point reflects back parallel to the axis. And the next one, the ring that strikes the center of the mirror reflects at an equal angle on the opposite side of the optical axis. Yeah, and the step 5, extend the rings until they converge. The rings converge at the image point. Draw the rest of the image in the image plane. If the base node object is on the axis, then the base node image will also be on the axis. Yeah, and then lastly, measure the image distance as well. Also, if needed, like measure the image height relative to the object height. The magnification can be found from equation 80.9, like m equal negative s dot equal s. Yeah, that makes sense to you. Okay, yeah, this is how to do like ray tracing for concave mirror. You can see it's a similar steps for the ray tracing for a convergent lens, divergent lens. Yeah. Okay, let's continue to talk about like convergent mirror. There is one example, finding the image location for a convergent mirror, like a 3 centimeter high object is located 16 centimeter from a concave mirror. Yeah, the mirror's focal length is 40 centimeter. Use ray tracing to find the position, height, and magnification of the image. Yeah, actually, yeah, let's try to talk about strategy. The image is further from the mirror than the focal length. You can see here is the here is the object. Yeah, this is and this is the focal length. Yeah, and the image is further from the mirror than the focal length, so we will expect the image to be real and inverted as for a convergent lens, and as in the figure, like this. Yeah, so this is the step. You can see the first one, and just lay out the optical axis with a scale. This one, and the step 2, and draw the mirror and a mirror plane and make the focal point here. And the step 3, draw the object as an arrow with its base on the x. Yeah. And step 4, like draw the 3 special rings from the tip of the arrow. This one, yeah, and just go to the focal length. And this one is just go to the center and the same angle. And this one is just go through the focal length and then parallel to the, yeah. You just draw the excitation line, and then it will convert to one point. This point is just this point, for the real image for this point. Yeah. So this is the steps for like how to do the ray tracing to find for the like object. And the figure, yeah, those figure we just talk about this from step 1 to step 6. The figure shows the ray tracing diagram and the steps tactics box 80.4. Yeah, and how to solve it. And after, yeah, you can see here. Yeah, we know. Yeah, this scale is 10 centimeter, and this is 16. I think it is yeah, 16 centimeter. This is yeah, as it's 16. And then you can see if you here you want to find the stone, right? So which means you just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's just 20, 120. Yeah, and then you will know like the yeah, you can use a ruler. Oh, yeah, you can use a ruler to find out the image position is around like 120 centimeter. The magnification is thus like m equal, because it is a real like image, so it is just the positive value. And then you use this equation and to find the magnification is around like a -2. Yeah, the negative sign indicates that the image is inverted. The image height is thus twice the object height, or h dot equal 6 centimeter, because the original like object is 3 centimeter high. So yeah, the object, the like real image object is twice, so it is 6 centimeter. Yeah, let's assess this results. Yeah, the 3 special rings converge at a single point, and the image is real and inverted. as we expected. This gives us confidence in our results. Does it make sense to you? Okay, let's continue. Okay, we have already talked about the convergent mirrors. Let's continue to talk about divergent mirrors in a detail. The divergent mirrors show a small upright image. You can see this is a typical diverging mirror. It shows a small upright image. Divergent mirrors are often called convex mirrors. Yeah, convex mirrors are used as a passenger side rear view mirrors, and you can see if you observe your car, your car's front mirror, like outside front mirror, you will see it is a convex mirror. Yeah, actually it can see more things. Yeah, but it is smaller. Yeah, the convex mirrors are used as a passenger side rear view mirrors and in stores to keep an eye on customers. Because the image is smaller, you can see much more of it. Yeah, you can see much more things, but smaller. Okay. And yeah, this is like the 3 different rings for divergent mirrors. Yeah, and the first one is any ring. Yeah. Sorry. Yeah, any ring initially parallel to the optical axis will reflect as though it came from the focal point. You can see there are some like parallel rings, and it will diverge away from the mirror. And if you extended those lens, those divergent lens, it will converge to the focal point. Yeah, it seems like it came from the focal point. And this is the second ring, like a second type ring. Like any ring initially directed toward the focal point will reflect parallel to the optical axis. Yeah, you can see those lens. Yeah, just direct toward to the focal point, and then they match the mirror, and they will reflect. And yeah, it will reflect, and those reflect. If you yeah, like it will reflect as a parallel. Yeah, this is just an incident line. And if you extended this incident line, it seems goes towards the focal point, and then they will inflect to the parallel, to parallel lens to the optical axis. Yeah, this is second type. And the last one is any ring directed at the center of the mirror will reflect at the an equal angle on the opposite side of the optical axis. Yeah, actually this one is the same thing with convergent mirrors, but these two are, yeah, these two are different. Yeah, it's just similar with convergent lens and the divergent lens. Yeah. Okay, let's continue to talk about divergent mirrors. We use the 3 special rings to show that no rings converge at the image point P dot. Yeah. You can see here, those are 3. Yeah, 3 different lens. And if you this is a reflected lens, and if you extended it, and you can see those extended, yeah, it will converge at the image point P dot. Yeah, but if you just use this, not like a extended line, it will not converge. Yeah, it will diverge. Okay, the divergent rings appear to have come from the P dot. Yeah, you can see it come from. The image is upright and much smaller than the object. Yeah. Does it make sense to you? Okay. Let's continue to talk about it. And yeah, this is for how to do the ray tracing for a convex mirror. Yeah, from the step 1 to 3, actually it's similar like with the like text box 80.4 like firstly just firstly just like draw an optical axis and center the mirror on the axis and represent the object with an upright arrow at a distance s. And from the step 4, and it will be different because three three special lengths is special lengths are different. Yeah, draw the three special lengths from the tip of the arrow. Use a straight edge or ruler. The lens should reflect off the mirror plane. Yeah, there are three different lens. A lens parallel to the axis reflects as though it came from the focal point. Yeah, a lens initially directed towards the focal point reflects parallel to the axis. And the last one, a lens like that strike the center of the mirror reflects at an equal angle on the opposite side of the optical axis. We have already talked about those three kind of rings. And yeah, the step extend the emerging rings behind the mirror until they converge. Yeah, the point of convergence is the image point. Yeah, draw the rest of the image in the image plane. If the base of the image object is on the axis, then the base of the image will also be on the axis. The next step measures the image distance as drawn. Also, if needed, measures the image height relative to the object height. The magnification can be found from equation 80.9. Yeah, actually, it's the similar steps. Yeah, let's do some. Let's review some questions. And for this question, you see an upright magnified image of your face. When you look into magnify cosmetic mirror, the image is located. Which one? Yeah, in front of the mirror surface. B, on the mirror surface. C, behind the mirror surface. Only in your mind because it's a virtual image. Yeah. Actually, if you use a magnifying cosmetic mirror, which means you just make it like a magnify it. Yeah, so it should be behind the mirror surface. Yeah, that makes sense to you. Yeah. It, yeah. It Okay, let's talk about more about why it is behind the mirror surface. Yeah. Yeah, actually, like a magnifying cosmetic mirror is usually a concave mirror. This time of mirror, like yeah, it's this kind of mirror. Yeah. Yeah, this kind of mirror curves inward like the inside of a ball. Yeah, if the object your face is close to the mirror, like closer than the focal point. Yeah, like I just analyze. Sorry, I just analyzed. It's not here. Sorry, and I analyzed here. Yeah, it will have a like a virtual image in here and but it is bigger than the original one, which means it is in the yeah, behind the mirror surface. Does it make sense to you? Okay, let's continue. Let's talk about a conceptual example like a driver and a passenger mirrors. Yeah, the rear view mirror on the driver's side of a car is a plain mirror, flat mirror, while the mirror on the passenger's side is convex. Why is this? Yeah, the main reason is that the driver needs a wide field of view from both mirrors. he sits close to the driver's side mirror, so it appears large and can reflect the fairly wide view of what's behind. The passenger side mirror is quite far from the driver. Yeah, like let's point some let's mark some important thing, because the driver needs a wider field of view from both mirrors. He's close to the driver's side mirror, so it appears large and compared fairly. Yeah, the passenger side is quite far from the driver, so it appears relatively small. If it were flat, it would offer only a narrow view. The diverging mirror gives a smaller image, which allows the driver to see more of what's behind the car in this smaller area. Does it make sense to you? Okay, let's do access for this example. The next time you are riding on the passenger side of a car, compare the view in the two mirrors. The new perspective will let you see the benefit of making the more distant mirror a divergent mirror. This is one problem with the image in the divergent mirror, though. The image is smaller than the object, so the driver may perceive it to be more distant than it actually is. This fact is the reason why, for the warning on the passenger side mirror, objects may be closer than they appear. So sometimes you feel it's far, but it's not that far. So when you want to get back to the original road, when you want to speed up and pass through this one car, and you need to pay attention to this. Yeah. Okay. Let's talk about the other term. We call it the thin lens equation. Okay, let's talk about what is a thin lens equation. The thin lens equation is a mathematical expression that relates three fundamental quantities of an optical system. Yeah, that it is firstly it is a mathematical expression, and it relates three fundamental quantities of an optical system. The first one is the focal length, yeah, f, and the other is the object distance, s, and the image distance, s dot. Yeah. Here, yeah, we know here is a far focal point. This is a convergent lens. So this is the near focal point. This is a far focal point. This is a focal length, and this is the object distance, s, and this is the here. This is the image distance, s here. So the thin lens equation is about the relationship between those three things. Yeah, and because the two shaded triangles are right angles, the angle theta must be the same for both. Yeah, the triangles are similar. Yeah, this yeah, this is the theta, and yeah, this is the theta. These two triangle is similar. Are similar. Yeah, for similar triangles, the ratio of any two similar sides are the same. Yeah, which means here this is h. Am I right? Yeah, it's the same thing. This is h. This is h dot, and this is focal length. It is f, and this is what s dot divide minus f. So we can get this equation: h dot divide h to equal s dot minus f divide f. We have also shown that h dot divide h equal s dot divide s. Yeah, based on we have already shown through this before. Yeah, and let's talk about why is it that you to review it. Yeah. You can see this one here, this one we call it phi, and A angle A, and this one also angle A and M. So this is H dot, and this is H, and this is like S, and this is S dot. This is S from here to here, and from here to here is S. And those two angles, those two triangles, yeah, are similar. So it has this equation: H dot divided H equal S dot divide S. That makes sense to you? Yeah, we talked about this before. And in the thin length equation, the sine of the focal length can be, yeah, this equation is the thin length equation. And in this thin length equation, the sine of the focal length can be either positive or negative, depends on the type of length on mirror. The convergent length on mirror, the f is positive. But for the divergent length on mirror, the f is negative. We have already seen that with the magnification formula, the image distance S dot can be positive or negative, depends on the type of image. Yeah, real image that is inverted, so S dot is positive. And the virtual image that is upright, so the S dot is negative. Yeah, so this is what we learned before. And okay, let's talk about this synthesis 80.1. Yeah, this one is very important. We talk about, in this synthesis, we talk about lenses, mirrors, and their sine conversions. There are three distant image situations that can occur for lenses and for mirrors. We outline this here and give the sine of each quantity. Note that the object distance S is always positive. Yeah. Okay, let's talk about that. Yeah. For converged lens or mirror, the vertical length F of a converged lens or mirror is positive. Yeah. Because you can see the object, if the object outside the focal, like a focal point, this is the focal point, and this is like the image is real and inverted, and this is this is positive, and like the object is farther from the lens or mirror than the focal focal point. Yeah. And this is this is for the like convergent mirror. Yeah, it is like this is the image, real and inverted image is here. Yeah, these cases give real images that are inverted. The magnification M is negative. The image distance S dot, yeah, is positive. Yeah, you can see if this is positive, yeah, this is also positive. And yeah, this positive, yeah, it's positive. And if the object inside focal point, yeah, this is object inside the focal point, then there will be a virtual upright image. Yeah, and the object is closer to the lens or mirror than the focal point. Yeah, and these cases give virtual images that are upright. Yeah, also like the divergent lenses or mirror, the focal length f of a divergent lens or mirror is negative. For the divergent lenses and mirrors, there is no distinction between an object inside and outside the focal point. Yeah, there is no like no distinction between an object inside and outside. So it's a similar thing for the divergent lens or mirror. So yeah, they will have a virtual upright image for like a divergent lens or mirror. So these cases give virtual images that are upright. The magnification M is positive. The image distance S dot is negative. Yeah, we have already talked about this. And this is just a summarize for what we have already talked about. Yeah, you just know this. Okay. Okay, let's talk about some like a quick check questions. A lens creates an image as shown. Yeah, in this situation, the object distance S is is like larger than the vocal length f, or equal to the vocal length f, or smaller than the vocal. Yeah, which means here the image is inverted, so it is real. Am I right? So let's talk about what? Yeah, here. So it is what? It is the object should outside the vocal point. Am I right? So which means, which means it is larger than the vocal length f. Yeah, that makes sense to you. We have already talked about this. Yeah, it is a. Okay, let's talk about the other one. A lens creates an image as shown. In this situation, the object distance s dot is what? Yeah, it just asks you the object distance s dot, which means this distance. Yeah. Okay. It is larger than the focal length f, or equal, or like smaller than the focal length. Yeah, it just like yeah, the similar thing. It just let you, yeah, because the image distance is positive, and it is yeah, it is just this situation. I'm right. So which means it is larger than the larger than the focal length. So it is A. That makes sense to you. Okay, let's talk about this one. Lecturings are conversion to point A, point one. Yeah. Lecturings convert to point one. The lens is inserted into the lens with its focal point at point one, which picture shows the lens leaving the lens. Yeah, which means you just put put the like the it this is the original one, and the lens is inserted into the lens with its focal point at like point one, which picture shows the lens leaving the lens, which means it will for the like for this is firstly let's talk about what's this. It's a divergent lens or the convergent lens. Yeah, actually it's a divergent lens. Am I right? Yeah. So for the divergent lens, yeah, for the divergent lens, if this is the two, which means those lens will parallel to the like optical axis. That makes sense to you. Yeah. So it is D. Yeah, because like for the because for the like divergent lens, the like rays they toward to the focal length, it will like through this divergent lens, it will parallel to the optical axis. Yeah, let's see if there are some. Yeah, you can see here. Here, yeah, it will like that it will optical. Yeah, it will parallel to that, and also yeah, if it is yeah. Does it make sense to you? Okay. Let's talk about this one. A lens creates an image as shown in this situation. Yeah. What's the relationship between S and vocal length and yeah, like so for this situation, we know like the S should greater than like a focal length. Does it make sense to you? Yeah. So, but here we need to talk about the relationship between S and the 2F. Yeah, that makes sense to you. So, like because the image is real, so which requires S greater than F. We know that. The image is taller. You can see it's taller than the object, which means S dot should greater than S. Am I right? So which means S should be smaller than 2f. Yeah, that makes sense to you. Yeah, because if S greater than 2f, yeah, we know like S should like yeah, S should greater than f. Yeah, otherwise, yeah, this situation, for this situation, S should greater than f. Yeah, but how can we tell S is smaller than 2f? Actually, from the same length equation, yeah, we have like h dot h equal S dot equal S dot S. And from this equation, actually we can get we can have like we can have f we can have this equation, and if we let the s greater than 2f and put this into this equation, like which means the s pair smaller than s, but you can see from here the s pair should be greater than s because it is larger, the image is larger than the original one. So which means the answer is should be this one. Yeah, does that make sense to you? Okay, let's talk about the other one. Yeah, this question. In this figure, the image is produced by the lens. At which point is the lens? Yeah, this is the image, and this is the object. Yeah, so which one? Yeah, because this is a convergent lens with object inside focal point. So the lens should be here. It's just like this, but and the vertical point. Yeah, you can compare. You can put this thing to it. Now this one. Let me check which one. Which one? Which one? One moment. Yeah, this one. You can see this is this situation. Yeah, that makes sense to you. Yeah, so which means because this is the image and this is the object, which means here it will be a converged lens, and this object is inside the focal lens. Yeah, so the answer should be D. That makes sense to you? Okay, let's check one example, like analyzing a magnifying lens. Yeah, a step connector uses a magnifying lens that sits 2 centimeter above the step. The magnification is 4. What is the focal length of the lens? Okay, let's try to analyze this one. Since the image is larger, yeah, this is a focal point. Yeah, this is the step. This is the lens then, and this is the S. And this is a virtual image. Since the image is larger than the object, the lens must be a convergent lens. Yeah, and the connector looks through the lens to see the image. So we know that the image is virtual. This is a situation we've seen before. We know that the object is closer to the lens than the focal point, and that the image is upright. So this is the like a focal point. Yeah, this is the focal point. This is the focal point. Yeah. Okay. Like even though we have an equation to solve for the various distance, it's still a good idea to start with a range tracing diagram to help us to make sense of this situation. The diagram is showing in this figure. Yeah, you can see we draw this. This is the focal point. This is the focal point. This is the lens, and this is three different rays, and this one is just like parallel to the optical axis, and this is just go to the center, and this one is just goes to the from the focal point and then parallel, and those three extension, and it can be, this is just this point. Yeah, a virtual image is upright, so M equal like a positive 4. Yeah, it just give you that the magnification is 4. Okay, and the magnification is, we can use this equation. Thus, the S dot equal negative 4s equal negative 8 centimeter, which means this is 8 centimeter. Negative 8 centimeter. Yeah, that makes sense to you. Okay. So we can use S and S dot in the same length equation to find the focal length. Yeah, this equation, we have to talk about this from the equation 80.9, I think. Yeah, from this equation. Yeah, from these two equations, we can get this equation, and from this equation, and we know this is 2 and this is negative 8 centimeter, and then like we use this equation and we can get 1 divided f equal this one, and then we can get the focal length. It is 2.7 centimeter. Yeah, which means the f greater than 2 centimeter, greater than this one. So it is, which means our result makes sense. Yeah, as expected, because the object has to be inside the focal point. Okay. Yeah, this is what we talk about in this class, and we talk about the like the ray tracing for different like lengths and mirrors, the convergent lens and the divergent lens, the convergent mirror and divergent mirror. And actually the ray tracing like steps are similar, but just the three different spatial ranges are different. Yeah, so yeah, you need to pay attention to that when you resolve the specific problem. Okay, let's do a summary for this chapter. Yeah, this chapter we talk about, we mainly focus on the ray model of light. Yeah, and firstly we talk about reflection. Actually, we have to do a review in the beginning of this class. Yeah, this is a law of refraction, and the incident angle equals the reflected angle, and the refraction can be specular or diffusion. And for the plane mirrors, a virtual image is formed at P dot here. This is the distance for the object, from object to the mirror, and the distance from the image, virtual image, to the mirror. This distance are C. Yeah, okay. This is for the reflection, and for the refraction. Yeah, this is reflection. This is refraction. Just pay attention to that. And we mainly use the Snell's law of like to represent this refraction. Yeah, usually the refraction happens in two different materials. Yeah, this is material 1, this is material 2, and this is relationship between material 1 and material 2. The index of refraction is this one. We talk about this a lot. The ray is closer to the norm on the side with a larger index of refraction. Yeah. But please be attention, the angle, the incident angle and the refracted angle is just like this ray and the norm from this angle, not the surface. So be attention to that. If N2 is smaller than N1, if this one is smaller than N1, there is a situation total internal refraction occurs when the angle of incident theta 1 is greater than theta c equal this one. So yeah, Okay, let's continue. Yeah, there are some important concepts. And the rain model of lights. The light travels along straight lines called light rains at speed, this speed. And a light rain continues forever unless an interaction with matter causes it to refract, scatter, or be observed. The light rays come from self-luminous or reflective objects. Each point on the object sends rays in all directions. Yeah. The rain diagram uses only a few select rays to represent all the rays emitted by an object. In order for the eye to see an object, rays from the object or image must enter the eye. Yeah, actually we have already reviewed this in the beginning of this class. Yeah, so we also talk about some image formation. If rays diverge from P, yeah, and after interacting with a lens or mirror, appear to diverge from P dot, and without actually passing through P dot, and then the P dot is just a virtual image of P. If lens diverge from P and interact a lens or mirror so that the reflected rays converge at P, then P dot is a real image of P. Rays usually actually pass through the real image. Yeah, this is what we learn in this class. And this is 3 special rays in 3 basic situations. Yeah, the converge lens, this is for the real image, for the converge lens for the real image. This is converge lens for the virtual image, and this is divergent lens for the virtual image. For the divergent lens, there is no real image, just one situation. Okay. This is a rain tracing for mirrors, and this is for the lens. This is for the mirrors, but it's a similar thing. This is a convergent mirror, like this is the real image, and convergent mirror virtual image, and this is divergent mirror, the virtual image. Yeah. And this is the thin lens equations. Yeah, actually, I didn't put it in the when we talk about the thin lens equation, but it's very easy to get from what we write it down. Yeah, for lens or curved mirror, the object distance s, the image distance s dot, and the focal length f are related by the thin lens equation. This is the thin lens equation. And the magnification of lens or mirror is this one. We talk about this. And the sign conversions for the thin lens equation, just like this. Yeah. If for the s, it is always positive. Yeah, this is the distance from the object to the lens or the mirror. And yeah, and for the real image, like on the opposite side of a lens from object or in front of a mirror. And for the virtual image on same side of the lens as object or behind the mirror. And for the vocal lens, it is for the convergent lens or mirror it is positive. For divergent lens or mirror it is negative. And for the magnification, if the image is upright, it is positive. The image is inverted, it is negative. Yeah, so this is for the sign conversions for the thin lens equations. Yeah, that makes sense to you. Yeah, this is all we talk about in this chapter. In this chapter, we mainly focus on the rain model of light. Yeah, if you have any question, just let me know. Okay. So yeah, this is today's content. Yeah, I know it's a lot, but try to remember the most important thing. Yeah, and try to relate this theory with the real world example. Yeah, it will help you to understand all these things. Okay, see you. Bye.